Okay. So we'll quickly cover sort of the last part of this, which we also get into a little bit more of in the part two of the lecture. So kind of once you've done the segmentation, the first thing you can do is kind of this shape analysis. One of the other things you can do is this meshing step. And so if we look at the data that we had sort of before, we had sort of these black and white pixels. We've now clustered them into group. And if we want to quantify something more interesting in this data, we can start to look at the mesh. So where is the surface of this object? And then if we think about a lot of sort of physical models that we get into, when we look at the pixel-based representation, we don't really have any quantification that we can do with how hard it is to turn a pixel off. And so if we were to take this image that we have up here, and we were to try to like compress this object, using a pixel-based model wouldn't really tell us very much, because how hard is it to turn that off or to stretch it and turn this one on, for example. And that's very difficult to estimate with this sort of image. And so that's why we can do something like make a mesh of our object, which then allows us to focus on sort of what are the vertices in the objects and what are the edges. And that you can now look at each edge and use sort of a very simple like spring model from high school physics, where you can say this is the natural length of it, and the force it exerts is the length you change it to minus the natural length. The natural length minus the length you change it to, and it's proportional to how much it's stretched. And so you can now begin to take your images and do compression and stretching and more physical-based analysis of them, rather than having sort of voxels or pixels that you need to turn on and off. And so basically how meshing works is, each exposed face of a voxel belongs to the surface, and we can add each exposed face to a list of sort of all the surface squares that we have, and then just add sort of the connectivity information. And so there's obviously many, many different ways of doing this, and they get covered in sort of a huge amount of detail in image-based meshing, and anyone who works with finite element modeling will cover this in much more detail than we cover here. The only approach we'll briefly mention is this idea of marching cubes, and that's because it's a very useful tool that we'll use over and over again, where we can see that looking at the voxels as an approximation for the image is very poor. And so if we go back to this simple image here, basically the first approach was to say that the surface of the object are just all the edges that are exposed, and to be like tracing an outline of all of these voxels. And the problem with that is the object itself probably doesn't have these sharp boundaries on it. That the object itself is probably sort of a smooth line connecting these things together. And we only see these sharp boundaries because that's the pixel representation that we have. And so using the pixel representation as if it were the real object kind of gives us a false impression for kind of how sharp the boundary is, because we don't expect it to be perfectly flat here, and we don't expect it to be incredibly sharp at those points. And so what marching cubes lets us do is have sort of a simple approach. This article got deleted. Anyways, because Wikipedia changes. Of looking at all the different possible combinations and trying to predict which surface makes the most sense at each point that we look at. And so rather than taking each surface as sort of the voxel boundary itself, we look at, if this pixel's on and this pixel's on and this pixel's on, then you have a face that looks like this. If these four are on, then you have a flat surface. If these three are on, then you have this surface. And so it's basically how you interpolate these voxels you have into all the different polygon configurations so that you get boundaries that sort of make sense. And so what that gives you is that you can get sort of smoother surfaces of objects, and this is then obviously used in 3D animation or making nice reconstructions from images. And we'll cover that in more detail. detail. And so now we'll go to the sort of next lecture, the part 2, where we go into a bit more detail on these things. So we can try doing this again. So again, we have similar references. We have a few more papers and sites to look at if you're interested. So the techniques in sort of thickness and curvature and radiomics are interesting links to look at because, again, we just briefly cover those topics. And so if we go to the motivation, that kind of fits into the end of the last lecture, that we've covered some of these initial techniques, but they're not always providing us all the information that we need. And so now it's kind of how can we measure sizes in complicated objects. And so before we measured, how we could find sizes and dimensions that work for these kind of simple cell-shaped objects fairly well. You can find a bounding box, you can find the area, the radius, all of those terms make sense for these kind of objects. But how do we do it for objects that are more messy and more complicated? Then kind of more particular for mechanical engineering or material science problems is sort of how do you measure sizes that are relevant for things like diffusion or chemistry? How can you quantify how fast things could diffuse through large structures? A little bit more in surfaces and how we can kind of quantify surface shape and shape of complex objects as they grow. And so if you're looking at a lot of objects as they change size, how can you characterize what the shape does while the size is changing? And then from texture analysis, so how do we quantify patterns inside of images? How do we compare different patterns? And so beyond just kind of like a simple thresholding of like looking at what the sort of regional associations inside images are. And then one of the things that if you've worked with radiologists a lot, they'll say about images is that some images or some lesions look evil. And of course, being a quantitative class, we want to come up with what sort of metrics can we use to quantify looking evil, rather than having this sort of very qualitative phrase, which might be accurate or might be a useful diagnostic tool, but certainly isn't very reproducible or easy to measure on large numbers of patients. So the first technique we'll cover for this is sort of this idea of distance maps. And so if we look at kind of this simple image here, we have this, perfectly circular cell. And what a distance map lets us do is that we take each point in the map as the distance that point is from the given feature of interest. And so this could be the surface of the object, an ROI, a center of the object, etc. And so again, this is a function that is in scikit image, it's in Fiji, it's in 9, it's in MATLAB. And so it's a technique that comes up very frequently, and you should never have to implement it yourself because it's been implemented very well a number of different times by a lot of different groups. And so what we can do here is we can take the image and we can compute the distance transform. And so here we show the distance transform of the image, where each pixel now becomes the distance it is away from the boundary or the background. So here we see 1.0, there it's 2.0, there it's 2.2, 3.2. And so, this is 1.4 because it's a diagonal element. This is 2.2 because it's over that way. And so we have an easy way now of measuring how far things are from the surface. And this is then a very useful kind of pre-processing step. And so it's kind of a more powerful version of sort of erosion, because rather than actually deleting the data, it just tells us how far each point is from the surface or from the point of interest. There's a number of different ways we can compute it. So we have sort of the exact Euclidean distance. And so here we get this image in 33 microseconds. And so of course that's really, really fast. But when you start to look at images that are giant 3D volumes, the fact that it takes 33 microseconds versus 75 microseconds can have a huge difference. You know, that if you're doing a distance map on an image that's 2000 by 2000 by 2000, you know, it can take 2 hours to calculate a distance map. And so looking at techniques that are twice as fast makes a huge difference for how much time it takes to do your analysis. And so this is sort of the exact Euclidean distance transforms, this EDT. We then have a brute force algorithm. So this is the kind of running through each iteration one at a time, kind of like that labeling approach we talked about before. And this one takes 75 microseconds to run on this fairly simple image. And then we have the Kampfer type transform, which is able to do it in sort of 23 microseconds. And we see that it's not as accurate, so it's making some mistakes. So here it's 2.0 when it should be 2.2. Here it's 1.0 when it should be 1.4. But it's quite a bit faster. And so when we're dealing with larger images, using this technique, if we're not too concerned about small differences, can lead to kind of a huge performance boost in what kind of analysis we're doing. Yeah. So again, it doesn't really matter for small images that we're trying to show, but it matters for really big images. And, if you're not that concerned with really small differences, then using these techniques can lead to a massive boost. And that if you look at kind of the exact Euclidean transform, for this image, which is 500 by 500, this takes 28 milliseconds. For an SLS scan, this would take almost a half an hour. For this brute force one, it would take 8.6 hours to process one scan. And for this Kampfer distance one, it would take sort of 1/20th of an hour. And so clearly for these techniques, this is not giving us the perfect right result for the image, but it's giving us a result in a much quicker feedback loop. And so particularly for iterating and trying to explore, using these kind of approximate techniques can make our analysis much, much quicker. And that, this technique is accurate, but is much more efficiently implemented. And so, the order would clearly be to do this one first, to figure out if you're doing the right kind of analysis and figure out what parameters make sense, and then to switch to one of these two once you're confident if you really need that higher level of accuracy and precision. And so if we look at how this distance map actually works, we basically take our image and we divide it into two categories. We sort of have foreground and background. And so if we've done labeling, we can now choose one of these labels, or we can use all of the image before we do labeling, if that's what we're actually interested in. And so often this technique is very helpful in images that we can't label very well. And what we do is we sort of define this distance as the minimum distance between the point we have and the nearest point in the background. And so here we'll use sort of Euclidean distance, but there are lots of other metrics you can use. And so one of the most common ones is sort of this like Manhattan or city block, which if you were, Uber and you were trying to optimize how cars are driving, Euclidean distance isn't really relevant because you can't just fly with your cars yet. And Manhattan city block distance might be a more relevant metric. Obviously, distance on the streets that are available would be the best metric, but if you're on like a grid system city, this would be a fairly easy approximation to do. And so this is kind of what the distance iteration map looks like. And so if we look at the brute force implementation, it looks something like this, but basically for each pixel in the image, we go through all the neighbors and we kind of add the distance based on kind of what the closest point we have is and how far we are from that closest point. And so as you can imagine, you have 4, 4, 4, 4. So there's quite a lot of iterations going on. And of course, the larger your neighborhood gets, the more iterations you go through. And each time you have to kind of do a comparison. You have to calculate this distance, and so it's a fairly time-intensive operation to perform. And so what we can show here is that we have sort of our original image. And now we can do, just like with this component labeling, these sort of iterations so that we have our original image where it's all 255. And that as we go through, we set it to that distance based on sort of which points are closest to the edge and going through the minimum operation so that we get in 4 iterations our kind of final distance map out. And that you can see some of these values are refined as we go through, where these then go from 4 to 4.2 to 4 because they're moving sort of in each iteration. It realizes there's a more direct route to that pixel. And so what's quite nice about this technique is that when we go to the final result, if we want to know how far this pixel is from the edge, we just have this 4, and that tells us that it's 4 away from the edge. And it's looked at all the different possible routes you could go from the edge to this pixel, and this is the smallest one. And so if you were to try to compute this manually, you would have to go look for each possible route it could take and find the minimum. And if you use a distance map, it's sort of already done that for you. And so it makes that step a lot easier. And so it can be a very useful tool if you're looking at distances or you're looking at trying to measure distances in different shapes for calculating that efficiently. So if we use sort of the Manhattan city block metric, we have a slightly different loop. So instead of that Euclidean metric, we now have the absolute value in x and y that we just add together. And we get sort of the same sort of approach, where we go through the image, and we now get a similar looking map, but that we see, none of the diagonal values are smaller. And we obviously don't have anything but integers because we're just adding up differences. But we still have this value go from being, I think, 6 to 4 because it realizes we can go sort of a more direct route this way. And so one of the issues we have with distance maps that you'll particularly come up with in 3D imaging a lot is that we measure distances over pixels or voxels. And for them to have a physical meaning, and so when you say distance, you kind of implicitly assume it has some sort of metric associated with it, we'll need to convert these pixels or voxels into real space. And so if we're dealing with isotropic images, so in like X-ray tomography, we often get isotropic images, 1 micron by 1 micron by 1 micron, it's fine. But if we're dealing with anisotropic images, as you get with MRI, or even in hospitals, the CT imaging they do is often very anisotropic, then you can't really use distances, or you can't use the distance map as it is, because it's telling you how far something is in pixels, and a pixel in Z is a lot larger than a pixel in X and Y. And so you have to account for the fact that those are different dimensions before you use the distance map. And so you can't just apply a distance map to your CT image. You first have to make sure it's sort of isotropic. And so ideally, as part of filtering, you resample and you convert it to an isotropic scale. That's the easiest thing to do. And if that's not possible or that's too inefficient, then you'll have to kind of build your own custom distance map algorithm, which uses the side lengths to calculate the distance rather than assuming it's 1 by 1. So if we go, up here, we can see that, with this algorithm, we've manually implemented that the distance is equal to the absolute value of xp plus the absolute value of yp. And if we wanted to do this in an anisotropic way, we could go like 0.5 times yp. And that would then allow us to have a setup where it was accounting for the fact that the distances in x weren't the same as the distances in y. But then we can't use any of the pre-built functions that we have. We'd have to sort of write it ourselves. And so there's two distance maps we can make for each image. So one of them is the foreground to the background, and this gives us an idea about the object size in the interior. And the other one is the background to the foreground, and this tells us about the distance or the space between objects. And so if we take that same image, the distance map of the background to the foreground looks like this, and the distance map of the foreground to the background looks like this. And so none of these images are really useful examples of what a distance map can help you with. They're just trying to illustrate the technique fairly well. And so one of the useful components about distance map is that it's fairly insensitive to small changes in connectivity. And so if we remember the sort of component labeling slides that we went over, we had this example here where the 154 point, because it happened to be one shifted over here, is now counted as a separate object. And so if we were to look at the average object size in this image, we'd have a very big object, a medium-sized object, and then a super tiny object. And so this would bring the average size down significantly, even though it's just 1 point. And if we look at distance maps, we can look at sort of, the distance map. We could take the mean and the standard deviation or the average distance. And as we make these objects bigger, we can see that this average distance kind of gradually goes up, sort of as we'd expect. And if we do component labeling of these images, and we show the average area, as soon as these objects start touching, the average area spikes up, because now you only have one object. And so if you're trying to measure sort of small changes in your system, and you use something like component labeling, you'll end up with this giant jump when these objects touch. And that might not be what you're looking to measure. And so using something like a distance map would give you a kind of smoother metric for what's happening in your images. And so this might not be something necessarily that's happening with time, but if you're dealing with experiments where, if objects are exactly connected or not doesn't matter that much, then using a distance map is probably a better way to measure it than using a component labeling. But if you're dealing with an experiment where you're looking at like electrical circuits, then obviously one pixel being connected or not could be the difference between your circuit working or not. And so then using a component labeling approach would make sense because these connections have a huge impact on what result you're looking at. But if you're looking for something that isn't super sensitive to these exact connectivities, then using distance map or metrics based on it give you much more stable results as your objects change. And so now we kind of apply it to more interesting real images. And so if we take these kind of bone image we had before, we have this image, we perform some sort of nice segmentation, and now we end up with all of the sort of cells and blood vessels in the image. And so what we can use the distance map for, we can do the foreground distance map and sort of see the size of all the objects. And we can use the background distance map to tell us sort of how far apart all of these objects are. And so what's quite useful about this is we can now see that, if we were to try to find where's the biggest gap between cells. So if you were saying the cells are providing sort of bone development and bone support, where's the biggest gap between them? That you could quite easily look at this distance map and say, well, this corner up here and these corners down here are the sort of most devoid of cells. And so these areas of bone might be weakest because they're furthest away from kind of the osteoblasts that are building up cells in that area, bone in that area. Similarly, if we take this sort of the cortex image, we can do a distance map on it and sort of get a visualization for kind of what the object generally looks like. And so if we were to look at the shape tensor, that wouldn't really tell us very much because that's kind of an elliptical or sort of round object model. And by doing a thickness map, we can start to see that if we just took sort of all the yellow points, that would give us something of sort of the backbone of this object, and that we can look at the thickness and see that the thickness is kind of bigger here and then drops down. And so it gives us more useful representations of what we're looking at. And so If we want to utilize this information, it's a little bit trickier. So the distance map is rarely the last step you're performing. It's just part of an analysis. And so here, if we take that sort of cortex object, we can make a histogram and we can see, there's a lot of 0 pixels. We're probably not interested in those, but that we can see that, 50 is about as far away from the edge as we get. And so if you were looking at this object, you could try to calculate the radius by taking, the area here and, dividing by pi and then taking the square root to figure out what the effective radius of the circle would be. Or you could take the largest distance you have and say that's probably about the radius. So that this 50 corresponds to what the radius of that region of the cortex is. And so this is where we get to kind of next step, which is this idea of a thickness map. And so that rather than looking at just the distance map by itself, we go through the distance map, and for every point in the image, we try to find the largest sphere which contains that point and is entirely within the object. And so in sort of the example image, you have this point x, and the largest sphere is here that contains x and is entirely in the object. And it doesn't have to be centered at x, it just has to contain x. So actually any point in this sphere also has that, at least that same size sphere as the object that it's holding. And so what it tells us is, rather than what's the distance this exact point is from the boundary, it says what is the average kind of freedom around this point. So how much space is around this point on both sides. And what it's really useful for is when we're dealing with kind of spherical or tube objects, that it gives us an idea of what the radius is inside of these tubes. And so we can take this kind of simple implementation of a thickness function and now take sort of the foreground, and instead of having all of these different values inside the thickness map, the distance map, we have the thickness map which just has kind of the major radius. So instead of having a gradient, we now have that this object is mostly circular. Near the edges, there's some kind of rougher boundaries, but that it mostly has the thickness of this value. And that most of these other objects are also fairly consistent, that they have a fairly large sphere in the middle, a circle in the middle, and then some sort of narrower points along the boundary. It's then also quite useful for these sort of images, because we can now, instead of having these gradients, we now have an idea of how the sort of spread between objects is. And so the kind of average distance between the cells is sort of this yellow or green color, and that near the edges you have these much larger areas. And so it makes the histogram kind of much more meaningful for us. What is this? And that we can now look at the histogram of the foreground and the background. Did we have it before? And see what kind of number of pixels in the image had the given radius that we were looking at. Whereas before, when we were looking at just the distance maps, we had kind of this whole spread of all of these different values, which makes it really difficult to say what the actual radius is. And so here what we can do is we can just look at these values and say that there's 5,000 points which have a thickness of around 40, 3,000 which have a thickness between sort of 25 and 30, and it makes that analysis much simpler to do. It's also then quite useful for doing kind of 3D analysis. So all of these things we just showed on 2D examples, but we can also do them on 3D examples. So we have this example of sort of foam data, where we have all of these slices in the image, where with foam what you see is you just see the sort of the plateau borders in the image, so just where the water's collected, and you don't see the air. And most importantly, you don't see the boundaries between all of the bubbles because they're too thin. And so if we look at this image, because we can't zoom in anymore, you can kind of see the outlines of bubbles, but none of them are actually completed. And so if you did component labeling on this image, what would you expect to get? What? Yes, so you just get one component, and so it doesn't help you break up your image at all. And so this is why we need sort of another technique that helps us kind of break up our image a little bit more. That if we want to see, how many bubbles are present or what is the average size of the bubble, component labeling won't tell us that. And so here's what a 3D mesh of this image looks like. And so this is where we can use the marching cubes algorithm. And we give it sort of our threshold image. And then it's able to generate this mesh of what all the surfaces inside of this look like. And so when we look at the mesh, we can also sort of make out where we think the bubbles would be. And we can use another tool called Plotly to give us sort of more 3D interactive view of what this mesh looks like, but that we could quite easily see that we'd sort of expect a bubble to be here. We'd probably expect another one to be there, and that we see the water, but of course we don't see the faces, which would be things filling these kind of small holes. And that there's a number of applications, kind of all cellular materials that you look at will look a bit like this. And so what we can do is apply the distance map, which then lets us start to see where all the bubbles would be, so that we can see, all of these kind of green or red points would be the sort of bubbles in the images, because those are the points that are farthest away from the plateau borders, or farthest away from where the water collects. And that we can look at it along sort of the axial slices or along the sagittal slices and see that the bubbles are a bit more elongated in the sort of XY direction than they are in the XZ direction. And so now what's really useful about this is that we can take this image, which looks something like this if we sort of render it using Fiji, and apply the thickness map, which now gives us kind of a visualization of each bubble and how large it is. And so the thickness now tells us, if we know the bubbles are more or less spherical, what the radius of all of these bubbles are, and that we can quite easily say, either these tiny bubbles we ignore, or, count as just tiny bubbles, rather than having this image where we can't really count or assess anything. And so it gives us this way of sort of drastically simplifying the data that we have and getting something useful out of it. And so what we can do is we can use these tools where we can go through the distance map and sort of find the local maximum, which sort of correspond to these spheres, and now calculate sort of where the bubbles are in the image. And so this is just projections along the X, Y, and Z direction. And now we can take all of the bubbles that we sort of have and look at them quite easily. So if you run this on so if you run it on your computer or in the browser, you should be able to see these. So there's another tool you can use to look at 3D data, and you can sort of rotate around and explore the images and sort of see all the bubbles that you can find by using sort of the thickness map in the image. And so that you can get this export out and play around, change transparency and brightness and all of the other settings that you have, and sort of explore the data set a bit more easily that way. But that basically you can use this to kind of interactively look at your data sets. So similarly to a lot of these analyses we've done before, you have this sort of idea of interfaces and surfaces. And so this falls into some of the meshing work that we've done. But when you're looking at objects, you're not always interested in just where the boundaries are. you're interested in sort of where two objects are touching each other and where these interfaces are located. So like with the bubble example that we had, you couldn't see the actual boundaries between the bubbles. And so you want to be able to recreate the bubbles and then look for the boundaries by what's touching other objects inside it. And so, if you're able to do a segmentation and identify volumes in 3D or areas in 2D, the interfaces we're looking at are sort of one dimension lower. And so in 3D, this is called surface area. In 2D, this is called perimeter. And so you're able to look at what things are touching or what things have sort of common neighborhoods once you've done the segmentation and labeling. And then you can start to analyze, connectivity, if you're looking at sort of cell networks or electric circuits. For material science, there's a lot of coarsening or rheological behavior that's very determined by the surface of an object rather than the volume itself. And obviously, any chemical bound processes are looking at sort of surface bound diffusion or catalyst action, where the surface area is sort of the driving force in that. And so we can see surface area and perimeter as sort of a very simple analysis, where we do, just one dilation or erosion in order to get just the area at the boundary. And so if you take an image, you dilate it once, and you subtract the image from that dilation, then you have just the boundary pixels that were added when you did a dilation. You can similarly do that with erosion, where you erode it once and subtract that from the original image, and you just have the boundary pixels. Then we have these meshing, which we covered before, and then this idea of kind of curvature. And so when you're looking at sort of these surface areas or these boundaries or these meshes that you've created, you can analyze curvature, which is just looking at sort of how strongly curving a surface is. And mathematically, the curvature is sort of defined as 1 over this radius. And then, so a value with a very large radius would have a very small curvature, and a value with a very small radius would have a very high curvature. And that with curvature, you can visualize kind of like the surface normals. And so for a 3D object at each point on the surface, you create a normal that's pointing out away from the center of that object. And that's how you define the curvature. And so you basically take this normal and you look along all the directions and you find sort of the maximum amount of curvature and the minimum amount of curvature. And that's this sort of kappa 1 and kappa 2. And then from that, you can calculate mean curvature, which is just the average, and Gaussian curvature, which is the product. And so if Gaussian, if it's positive Gaussian curvature, which means sort of the curvatures agree in sign, that kind of indicates that it's sort of a sphere. If it's negative, it's then sort of a saddle. That means it's sort of curving up in one direction and curving down in the other direction. And if it's completely flat, then it's 0. And so here you can take images and you can color them by the curvature. Right now, as far as I know, none of this analysis is directly implemented in Python or 9. I think Fiji has a plugin to do it, and ParaView has a plugin to do it. But it's just an important technique to have heard of, because there are some problems where it is very useful. And so here's a tool called ParaView, which we have an example of in the exercises, where you can now show the mean curvature in this surface and sort of see where the sort of large negative curvatures are, or the large positive ones. Or you can show the Gaussian curvature, where you can see sort of, again, large negative, large positive ones, and start to characterize things as, characteristic shape. And it's a useful technique to at least have heard of. We won't really do much of it in this class, but there certainly are problems where it makes sense. Sort of the biggest problem with curvature is that it's very sensitive to your segmentation. And so if you have small errors or small changes in your segmentation, you can have massive amplifications in the changes in your curvature. And so, of course, there's lots and lots of other techniques. And so if you've ever used Fiji or KNIME or MATLAB, you see, Fiji. In the plugins menu, thousands and thousands of operations that you can perform. Some of them are useful. A lot of them are not that useful, or are only useful for very, very specific applications. If we go to Fiji, You can go through the plugins menu and you have hundreds and hundreds of plugins, and this isn't even all of the ones that you can start. I mean, there's many, many more that you can download in addition to this, and a lot of them are very useful to explore, but we won't really go into them in very much detail. And so here, for example, the UNet that we talked about at the last lecture, you have tools for using that or fine-tuning it or training it, all within Fiji. And again, with Python and KNIME, it's more or less the same. You have a huge number of these tools available, and that a lot of them can be very useful given certain types of problems. And so they're certainly worth looking into if you have the time, but we won't have time to cover all of them in the class. So the last quick thing we'll cover is this sort of idea of texture analysis. And you can read more about it here, where they kind of go into more detail about how it's defined. We'll just cover it for sort of a fairly simple example. And basically what we have is this idea of this sort of sample texture and co-occurrence matrices. For whatever reason, these didn't render. So of course you can always go to the old versions of the slides, and some of them have different representations than we had in this class. If you're interested in sort of how this is iterated over the years. For whatever reason, the single object. I thought it was one of these that had it rendered correctly. Or actually, since we're low on time, we'll just cover that at the beginning of next lecture. I'm not sure why it didn't show up correctly in this one. I don't see any examples there. But yeah, we'll cover it at the beginning of the next lecture and not try to jam it in now. But yeah, for whatever reason, that didn't end up rendering. Okay, so I'll look into that later. And texture analysis we'll cover at the beginning of next week rather than trying to jam it in. So are there any questions on materials so far? And in terms of the pace, so we've tried to sort of double up on lectures to go faster because there were a number of people who thought the pace was too slow, at least in the online feedback. Is it better now? Too fast? Do you want it even faster? No. Okay. Yeah?
Kind of depends like how, like sometimes you went over the slides quite fast.
Yeah.
And so the question is like how detailed one has to remember. Okay, like I'm taking notes now for everything, but like for example with the curvature it was just
Yeah. So the curvature you don't need to know anything about. Curvature, you should just be aware that it exists. And for certain problems it can be very useful.
So like the take-home message.
Yeah.
Okay.
So for curvature, so when there's a take-home message, that's all the things you really need to remember. It's just more of, so again, this class is meant much more for you than for passing the exam. I know that's not really the approach most classes have, but this class is supposed to be useful so that you can solve the problems you have to deal with better. It's not meant that you take this class so that you pass the exams. I mean, yes, obviously it's important to study for the exam and learn the material, but ideally the most valuable thing you can get out of this class is being able to actually solve problems and have an awareness of what tools are available. And so kind of the exam is structured very much in that way of how do you take a problem and solve it in a kind of sensible way. Not are you able to remember that kappa equals 1 over r and the mean curvature is kappa 1 times kappa 2 in the Gaussian. I mean, those equations are pretty irrelevant. You'll probably never need them unless you have a problem where you really need curvature to solve it. And so memorizing that isn't very useful. But knowing if you had some sort of wavy surface, that curvature might be a tool that would help you quantify what's happening or quantify changes in it is what's important. So for the things that are covered in much more detail, you're kind of expected to have a bit more understanding about that method than things that are covered fairly quickly. Curvature is just covered because there's a number of cases where that's really, really useful. And for almost all material scientists, curvature kind of plays a fairly important role. And so you want to be aware of it. We don't go into too much detail because it's fairly difficult to do and it's very problem specific. And so the techniques we cover in detail are techniques that tend to be usable over a broad scale of problems and don't require a huge amount of coding or specific tooling to use. But yeah, I mean, a lot of the what you're supposed to get out of it and what you are expected to be able to do at the exam is, can you bring these concepts together and sort of say this would be a problem where that would make sense, and that's sort of what it would tell you, and this is how you would evaluate that it worked well, and much less on the, can you derive this formula? What's the most efficient implementation of this filter? All of that stuff's kind of irrelevant. But yeah. So for the things that I go fast over, you're expected to know less about them. But many of you might have problems where that makes sense to go into more detail, and so at least having heard of it is useful, even if you, don't learn all the details and complicated analysis in this class. So yeah, okay. So if you have any